Ever wondered how a GPU can execute thousands of threads at once? By the end of this video, you'll understand the secrets of SIMT execution, how a single instruction manages massive parallelism across all threads. We start with scalar execution, the traditional approach where a single processing unit handles one operation at a time. One instruction flows through the pipeline. Data enters, gets processed, and results emerge. Simple, sequential, and limited. Now watch as we unlock true parallelism. Multiple execution lanes activate simultaneously, each processing different data with the same instruction. This is SIMD, single instruction, multiple data. A per lane mask selectively disables inactive SIMD lanes, preventing computation and write back for those elements. This is particularly useful when the number of data elements is smaller than or not a multiple of the available SIMD lanes, allowing a single instruction to safely operate on partial vectors without special case control flow. SIMD is the foundation of parallel computing. One instruction is broadcast to multiple lanes, each operating on different data simultaneously. This pattern is what makes GPUs so powerful. Let's transition from this abstract concept to how GPUs actually implement this pattern. Imagine we have 128 elements to process. We can divide them into groups of 32 elements each. If our hardware can process 32 elements at once, we complete the entire computation in just 4 execution steps. Watch each batch execute in sequence. Batch 0 processes elements 0 through 31. Then, batch 1 handles 32 through 63, followed by batch 2 with 64 through 95. And finally, batch 3 completes 96 through 127. These batches stack together, representing how the hardware organizes parallel work. Each stack contains 32 parallel operations that execute as a single unit. This example comes from the GPU programming model, which we will cover in detail later. For now, it is a simple kernel to build intuition about how threads compute unique indices and execute the same instructions on different data. This shows how programmer intent maps to SIMT execution. If this helps, consider subscribing. Now, let's continue. The kernel is launched, and registers are allocated for each active thread. Each thread loads its block and thread indices into registers to establish its execution context. Integer arithmetic is used to compute each thread's global memory index. Operands are loaded from global memory, the computation is performed, and results are written back. Here, the CPU instructs the GPU to execute the kernel with the given configurations and kernel parameters. Next, we move beneath the programming model into hardware. This is the Streaming Multiprocessor, where WOPs are scheduled. Remember, each instructions execute with a granularity of 32. A single instruction is applied simultaneously to 32 lanes, each with its own context. The SM has 4 processing partitions. Each includes a WOP scheduler, a dispatch unit, and execution cores. In this example, we show only the int32 execution units. The operand collector gathers input values for an instruction from registers and prepares them for execution. It is needed to ensure that all required operands are ready and aligned before an instruction is issued to the execution units. In this carefully chosen example, the optimal case assumes hardware scheduling evenly distributes the workload across execution partitions, allowing 128 elements to be processed in 4 parallel steps. Every partition has its own register file. ultra-fast storage holding thread state and intermediate values. With 64K registers per partition, each of the 32 threads in a warp gets its own dedicated register space for maximum throughput. Memory operations flow through specialized load store units. These handle all traffic between registers and the memory hierarchy, keeping data flowing to the compute cores. Let's zoom into one partition and trace how our kernel loads A and B, adds them, and stores the result. The kernel code is compiled into the intermediate representation PTX. The following snippet is a minimal, non-complete example included solely to illustrate register usage and memory instructions. Each PTX instruction expands into multiple SASS instructions, the GPU's native machine code. The compiler handles thread indexing, address calculation, and optimizes the instruction sequence for hardware execution. The partition is ready. Let's step through actual instruction execution and see data flow through the hardware pipeline, all 32 threads moving in lockstep. Special registers holding thread and block IDs, like thread ID and block ID, are moved into general-purpose registers. This sets up each thread's identity. Each thread computes its unique global memory address using integer arithmetic. IMAID calculates the linear index, and SHL converts it to a byte offset for memory access. When an instruction runs, it is applied to all 32 threads. But because there are fewer execution lanes than threads, the hardware runs them in smaller groups over a few cycles and combines the result so it looks like they all ran together. Now the first memory load. Each of the 32 threads sends its address to the load store units, which issue requests to global memory. And here's the critical moment. The entire warp stalls. Memory latency is 400 cycles, an eternity for the compute cores. This is why GPUs need thousands of threads. While this warp waits, other warps can execute and keep the hardware busy. Then the second load executes. Thanks to memory-level parallelism, this request can pipeline while the first is still in flight. Both loads proceed independently across all 32 threads, maximizing memory bandwidth utilization. With data finally in registers, the integer ALUs spring into action. All 32 threads execute their additions simultaneously. Operands flow from the register file through the operand collector to the execution cores. The addition completes in a single cycle per warp, lightning fast compared to memory access. Finally, we store the result. Each thread's address and data route through the load store units back to global memory. The write posts asynchronously, freeing the warp to continue. And that's SIMT execution. Single instruction, multiple threads. The GPU's secret is massive parallelism. Thousands of threads hiding memory latency, with hardware managing the complexity of scheduling, resource allocation, and synchronization. Each warp of 32 threads executes together in lockstep, implementing the SIMD pattern at massive scale. This architecture powers everything from graphics rendering to AI training, achieving computational throughput that CPUs simply cannot match.